Hey you guys, welcome back to the channel PHYSICSSIRJEE, and here we are in JEE Mains 2021 revision series that have started, and we have already produced 2 videos on it. And this is topic number 3 as promised in the voting section, that is thermal properties of matter. So this is going to be a slightly lengthy video like last time, but we'll try to cover up all the concepts that are very important for your JEE Mains based on the previous year's questions, and also some of the expected questions which I'll include as the new practice problems, as you could see on the right side of your screen, and the solutions of which would be provided after this video is done, or also in the comment section as you start attempting and commenting about them. Okay, so without much further ado, let's move forward. Let me tell you, when I say thermal properties of matter, I mean thermal expansion, calorimetry, and heat transfer, which takes up the chunk of the syllabus in previous NTA conducted papers. Okay, so we'll go in the same order. We'll try to see all the questions that have been asked in the past, right? The repeated models, and how the JEE mains people or NTA people have in the past constructed and conceptualized those questions. Okay, so, and those who are looking for new problems, and I have included the past practice problems at different levels, right? Starting from JEE mains and also slightly going ahead and challenging you for even JEE advanced and Olympiads. Okay, so in case you are new to this particular channel or the series, I would request you to watch the announcement video of this particular series, the link of which is in the description below, right? And why the PYQs, that is previous year's questions, are very important, how often they are repeated, and with the new announcement of the syllabus being changed, right, how important it becomes. It has been explained very clearly and thoroughly about the strategy that is required in the last 45 days of your preparation. Okay, so please do go through that one. So here we are. One more important thing that always bugs the students in the last leg is either due to lack of proper teaching at their coaching centers or mentorship, or because of the lack of interest of the students, the extra syllabus part gets left out by the students. So, and in the last leg, it becomes very difficult for students to actually get it covered. And one of the best things again you can do is to follow the previous year's question papers, especially the 2019 and 2020 papers, which have been conducted by NTA. Before that, CBSE used to conduct exams. So you could actually start with the 2020 and 2019 papers. I've tried my best with whatever little time I had in the past to cover the extra topics, both concepts wise and questions wise. As you could see, all the extra topics or extra syllabus parts I have written down here, and I have made a playlist of these videos. There are somewhere around 5 videos containing all the 2019 shifts papers of all extra topic questions, and 2020 the January shift. As you could see, the September 2020 shift questions I will add at the end as we go closer to the exam in February. Okay, so here it is. So let's start with the first question: thermal expansion. Two different wires having lengths L1 and L2 and respective temperature coefficients of alpha 1 and alpha 2 are joined end to end, then the effective temperature coefficient of linear expansion is. So in case you're new, I've already told you in the past videos that your best way to process this particular video to your advantage is to have a scribble pad and a paper and pen, and just like in your actual JEE mains exam, and pause the video at every point, try to read the question on your own and attempt it for 20-30 seconds, and then only move on for the concept and the solution explanation I'm going to give. Okay, so that's how we are going to go forward. Okay, so this is very pretty simple problem. I think the two things that are connected in series, the end-to-end connection means series connections, right? When you are heating it up, the effective length can be taken as initial L1 plus L2. So that L1 plus L2, which is L equivalent 1 plus alpha equivalent delta T, which is the new length upon heating it by a temperature rise of delta T, should be equivalent to the individual heating. Remember, this is free ends, so they'll expand as if the other rod is not present. Okay, right? So that's what we have written, and by writing L equivalent is L1 plus L2 and rearranging, it's a pretty straightforward and a neat result of alpha L1 L1 plus alpha 2 L2 by L1 plus L2. A straightforward one. Okay, so A Bakelite beaker has volume capacity of 500 cc at 30 degrees centigrade. When it is partially filled with Vm volume at 30 degrees centigrade of mercury, it is found that the unfilled volume of the beaker remains constant as temperature is varied. If gamma beaker is equal to 6 into 10 power minus 6 degrees centigrade inverse, and gamma of the mercury is also mentioned, where gamma is the coefficient of volume expansion, then the value of that Vm, which is the partial filling in Cc, is close to. As I already told in the past, these close to kind of questions are quite irritating in the exam because the calculation involved would be slightly on the tougher side. So it's better you try to push these questions to the end of the exam, try to attempt much easier questions. Also, in case there is a choice provided in the exam, I think you can leave such questions to the end, okay, until unless you have more difficult questions, try to not attempt these. Okay, so I'm not saying completely leave it, but push it to the end. So here it is, a simple idea about the apparent expansion. So if you have a beaker containing a liquid with unfulfilled volume, can you see there is a partial volume that is left out? Then what he's, according to the question, telling you is the total vessel volume minus the liquid volume should remain constant. That's what he's trying to tell. So just like the free expansion in the previous problem, the liquid and the solid will expand as if the other's presence is not there, right? You are not forcing them in any way. So when you are heating them together, they expand on their own as if they are independently present. So the beaker's expansion is written as an equation here, and the value of that particular mercury, right, liquid, that Vb prime is the liquid's volume, has also been written here. The subtraction of the two, which before and after, should remain the same. Okay, right. So when that, for that to happen, this term and this term should be equal to each other. Okay, so there's some small typing errors here, right? Vb minus Vb prime and V naught minus Vm should be equal to each other. So this should be Vm prime. Yeah. And this should be Vb prime. Okay, right. Yeah. Now this is perfect. And rearranging, you get the answer. Okay, so you could see that even though he said close to, in this particular problem, the solution is very simple. So at times what happens is that whatever tough looking question that is present, it could actually turn out to be easy, and that comes with practice. Okay, so let's move forward. A similar practice problem from the past papers, where a fraction of vessel is filled and some conditions will be given, and based on that you will be able to ascertain the requirement in the problem. Okay, so just pause it here, try to practice, and there is a solution in the next page, which I'm not going to explain. It's for your referral for the answer. Okay, so here it is, similar concept as you could clearly see, right? So another practice problem that I would like to take up, which is not the previous year's question, but slightly on a challenging level, is the one on the screen right now. So you want to give it a try, pause, read, attempt it for 1 or 2 minutes, and then go ahead with the solution I'm going to give. So a solid cylinder of height 10 centimeter is floating in a liquid in large container. The coefficient of linear expansion of solid is alpha, and the coefficient of cubical expansion of liquid is gamma. Initially, the cylinder is half submerged. Okay, so he has mentioned that. The temperature of whole system is increased by some amount. The height of the immersed portion will remain same if some conditions between gamma and alpha. The second question, the temperature of whole system is increased by some amount in another experiment, remember. The height of the portion of the cylinder remaining outside the liquid remains constant if and only if. Okay, so these are the two conditions. In first question, inner depth, inner submerged length should remain constant when you eat. And the second question is talking about the outer length, that visible length should be remaining constant. Okay, so I'll go ahead with the solution to the 17th. That is the first question. Okay, a lot of things on the board, just follow my lead, you'll be okay. So I have depicted the diagram on the right, where h is that inner length for the first question, which I require it to be constant. So when things expand, the L expands, and the object is going to therefore expand, but the value of the length that should be submerged should remain the same. Okay, according to this particular question. So here, since mg is equal to fb, you can write the value of the mg as volume of the body, entire volume, which is L cube, into density of body into G should be V submerged into rho liquid into G. This is the formula for the buoyant force, very standard one. So when you cancel out the volume of the submerged part, which is like a cuboidal volume, it would be nothing but H into L square, and volume of this is L cubed. So when you cancel these two, you'll end up getting H and L as factors. G gets cancelled. Value of H is this one. Okay, it's pretty simple. Now, in this format, you can actually write rho b divided by rho liquid as the factors, right? When you heat it, rho b becomes rho b times here. Can you see at the bottom of the screen? Rho b is rho b naught times of 1 minus 3 alpha delta T, right? Density decreases upon heating for a body. Okay, body's gamma is 3 alpha. Whereas for a liquid also, the density is actually going to decrease upon heating. So these are the factors with which it changes. And whereas L, that is the length dimension of that particular solid, is going to increase upon heating. So I have written. So all these written in form of factors, these factors should cancel out each other so that H doesn't change. So the product of all these factors in this format should be equal to 1. I think you could see on the top minus 3 alpha and plus alpha makes it a 2 alpha. And if the 2 alpha and gamma are equal, remember you can use binomial approximation here. 1 minus x divided by 1 minus y can be written as 1 minus x plus y, right? You can say 1 plus n x power n when x is very small is 1 plus nx. So I have used that. Let me write that on the side. So this is what I'm using. Is approximately 1 plus nx. You could see at the bottom. This is what we have used there. Okay, so gamma is 2 alpha. There is an alternative way of doing the same thing. You could say mg is constant, right? Because weight doesn't change. So you could directly say this is going to remain constant. So you could say V submerged, which I said is h square into L into rho liquid should be a constant. So from that also h square into L into rho liquid should remain constant. You can again rearrange the parameters only by looking at the constancy of the right hand side and still get the value of the H changes. Okay, so that gamma equal to 2 alpha is the correct solution. Okay, so let me mark the correct answer. This is the first one. So I think I'm well within my right to leave the second question for you. So I'll give the solution in newly formed series called PHYSICSSIRJEE Quickies, where I'll be providing solutions for quick concepts. Right, we can call them as very fast, short solutions for simple concepts. Okay, so this second one, try it out. Comment your answer below with the timestamp of the video so that I can reply to you whether you have done it correctly or not. Okay, so that's one way of communicating, and if in case you don't want to wait for the video solution. Okay, so let's move forward. This is a practice problem which is a multi-conceptual one. Okay, so this, I think you will enjoy solving this one. This is at JEE advanced level. You could say even at JEE mains level, slightly tougher one. Generally students get it a bit wrong here because it's going to contain even heat transfer concept also. So try to read through it and comment your answer with the timestamp below. So I'll be waiting for your answer. Okay, so let's move forward. This is another one, slightly more tougher. Students who are lookout for the international Indian Olympiad and National Olympiad series, right? So these type of questions fall under that. You can say even at the higher level of GA advanced. So please make sure that you attempt this question maybe for 2 or 3 minutes and then comment your answer below. Okay, so let's move forward. Now we are into thermal stress type of problems, and you would see quite often JEE actually is going to repeat this particular concept. Okay, so very important concept of thermal stress. A rod of length L at a room temperature and uniform area of cross section A is made of a metal having coefficient of linear expansion alpha. It is observed that an external compressive force F is applied on each of its ends, prevents any change in the length of the rod when its temperature rises by delta T Kelvin. Young's modulus Y for this particular metal is, okay, you should have got a picture of how he's doing it, right? So if you heat a rod, it actually tries to expand. But if you try to apply a compressive force and keep it not from expanding, then it is said to be in thermal stress. Okay, so it's very common idea. So on the simple concept, on the right side, I have depicted it in a nice superposition manner, right? So I would say, instead of keeping the object under some external force, if I were to leave it free and increase the temperature, then the rod would have expanded thermally in this format. Okay, L into 1 plus alpha delta T. Then I can visualize that this external force is then applied to compress it. So this gives you the actual feeling of the rod being under a compressive stress. What is this NL? NL is the natural length. And please understand, natural length is temperature dependent. It's not always L. At T, the natural length is L. At T plus delta T, the natural length is this. Therefore, at T plus delta T, if the length is L, then it is said to be compressed from natural length. So what type of stress or strain is it under? It is under a compressive stress or strain. So the value of the strain is given by the change from the natural length divided by the natural length. Actually speaking, the change is L alpha delta T, and natural length should be this number, strictly speaking. But most of the times in our calculations, we neglect this alpha delta T because of its order being very small compared to 1. Okay, so L gets cancelled under that approximation and gives you the strain value is always alpha delta T. So strain value is alpha delta T. So the stress is y into strain, and therefore you end up getting the value of y this way. Okay, so very simple concept. And you would see, I can't put all the problems that have appeared. I'll show 2 or 3 of them. But you would find in the previous JEE papers that it has been repeated quite a few number of times, and this is a very good mark scorer for students. Okay, so you could see repeated many times, same language, similar conceptual idea, no numericals in this case also. You could see it in another past paper. Many times I am not posting it here because of the length of the video. So why JEE is asking so many times? Because there is a lot of practical importance to this. So this is the diagram that I was talking about. When natural length changes and you try to compress it back, it is under a stress. Okay, so then one of the primary examples in real life where this kind of buckling happens with rail, right? So when these rails will be rods connected end to end or placed end to end. So during the summer season, when the temperature of these rails increases to very high degree, they try to apply stress on each other, and there is a not breaking stress, yielding stress as it is called. So once the yielding stress is actually crossed, then these rods yield or buckle or bend, and this kind of a picture will happen. And as you could clearly bet, that this is very dangerous situation for a train moving on that. So you could see on the right hand side, if the Young's modulus or the strength of that material is not good enough, this is what is going to happen. So you need to put those railings with some gaps between each other in winter, so that so as to allow the expansion in summer. Okay, so you could see this practical importance has been explored in other problem also. You could see that in the steel rail problem that again in 2017 they have asked, right? Okay, and read this. It is based on again the same idea of the thermal stress. Okay, so try to practice it. Basic question. Okay, and should be able to match this solution, right? So let's move forward. Another similar problem you could see from the past papers, wherein you have slightly different one, right? I could see that instead of having end-to-end connection, you have a semicircular ring, another touching another semicircular ring and allowing it to expand. So let's read through it. A wooden wheel of radius r is made of 2 semicircular parts. You could see the 2 parts are held together by a ring made of metal strip of cross-sectional area S. So there is a metal strip of S area cross-section. Length L. L is slightly less than 2 pi r. Okay. To fit the ring on the wheel, it is heated so that its temperature rises by delta T, and it just steps over the wheel. It's not steps over, it should be slips over. As it cools down to surrounding temperature, it presses the semicircular parts together. They press each other because of the touching each other. If the coefficient of linear expansion of the metal is alpha and its Young's modulus is y, the force that one part of the wheel applies on the other half of the wheel is how much? Very in similar question, but slightly more difficult as compared to if you are good at free body diagram. I think you should be able to ace this also. So I hope you have given it a try. I'm moving forward with the solution. So here it is. Try to compare your solution on the left side. I'll give you a hint. Okay, so the idea is to draw the lower half FBD when this one has a stress value, right, of F by S, then the force that it applies on the other one is F. So on the lower half's FBD, there will be two Fs that would be acting. So whatever calculations of Young's modulus you're going to use here and get the value of F, which is same as the previous problem. F is YA alpha delta T, A being S here. Don't forget to write that the total force is 2F, and that's the silly mistake a lot of students make. Because of the bending, there are two Fs here, so the answer comes out with a 2. Okay, that's the caution in this question. Okay, so let's move forward. Another one. At 40 degrees, a brass wire of 1 millimeter radius is hung from the ceiling. A small mass, capital M, is hung from the free end of the wire. When the wire is cooled down from 40 degrees to 20 degrees, it regains its original length of 0.2 meter. The value of capital M is again close to his given coefficient of linear expansion and Young's modulus and G. Okay, try this one out. I am moving forward. Okay, so here's the explanation. Very simple. You're hanging something, right? Then under the weight of this capital M, this wire has to expand, right? That is due to mechanical stress. Then you cool it, it tries to contract back. So it is under a thermal stress, and it is under a compressive stress, because under the temperature that you are having, you are going to have a longer, actually, sorry, smaller length, and therefore you are trying to compress it or expand it back. Therefore, there is a stress involved in that. Okay. So compressive or tensile is the word used for expansive stress that you should be able to make out. Okay, so I'll take back my word. Whether it is compressive or tensile, you decide. Okay, and you should be able to match the solution. Idea is very simple. The L alpha delta T, which comes from the expansion part of the thermal nature, it should be matching with the mechanical strain that has been produced. Okay, so that's why this equation has been written. And remember, I'm able to write this FL by AY because there is uniform stress. The weight of the wire has been ignored. How do you know? Because he has not given any weight for that. Only weight that is mentioned in the question is of capital M. It would have been more interesting if the weight of the wire was given and then the tension varies, and I've already produced the latest original series problem. You can go back to the thumbnails and check in last 3 or 4 videos. The latest PHYSICSSIRJEE original video was on a question where a rod actually had a non-uniform stress. Okay, so always identify the natural length at a new temperature and then calculate this. Pretty straightforward. I think you should get 6.28. Problem with this was it was a bonus question because such a simple calculation, the answer actually did not match to any of the options. So when that happens, your concept should be so strong that you should be very, very clear and not waste your time in the examination, right? That confidence you should have. It comes with practice. Okay, so let's move forward. This is a practice problem on thermal stress and elasticity. I'm going to answer this in AITS select series. In case you don't want to wait till that point, comment your answer below with a timestamp so that I can check and reply to you whether your answer is correct or not. This is definitely at a JEE advanced level. It is an interesting problem. Right? Not very tough, but not so easy also. Your concept should be very, very clear. So let's move forward. Now we are entering a topic of thermometry, where things about thermometers should be clearly known. It falls under the category of thermal expansion, right? But more practical approach is required. So a thermometer graduated according to a linear scale reads a value of x naught when in contact with boiling water, and x naught by 3 when in contact with ice. What is the temperature of an object in degrees centigrade if this thermometer in the contact with the object reads x naught by 2? A lot of different readings are given, and is asking the reading pertaining to the degree centigrade. Give it a try. I'll explain the concept behind the linear thermometry and then we'll look at the solution. I hope you're giving it a try. Let's move forward. First, the concept. What is meant by the linear scale? Here's a very simple explanation for that linear scale. So any centigrade scale or Fahrenheit scale or Kelvin or any other new standard scale, idea is very simple. Basically, you try to take two important points that are standardly known, like melting ice point and boiling water point, and try to measure those numbers and assume that during the expansion from 0 degrees to 100 degrees, the expansion takes place in a linear manner. So corresponding numbers in other scales with their divisions are marked, and equality is taken in the form of the linear slope. Okay, the two standard points define slope. Remember, a straight line graph, you need just two standard points to define slope. Once the slope is defined, every other point can be easily discussed. Okay, so what I mean is 0 to 100, when you actually increase it in equal manner, you could see the temperature increases between each of these two diagrams is equal, and the variation of the length is also in such a way that the graph can be considered. I will just try to draw and impress you. So the graph can be considered to be visually linear. Okay, so that is the equal slope concept, and that's why people prefer linear scales in thermometry. And I'm equating slopes here. You have the standard formula of slope of a straight line, y2 minus y1 by x2 minus x1, kind of a formula that you have written here. So for centigrade, the lowest point is 0, highest point is 100. Fahrenheit is 32 and 212. Kelvin is 273 and 373 approximately. There is a 0.16 also that is utilized there. And for any Z scale, let's say I'm defining a new scale called Z, then you have to write Z minus LP. LP is the lower point that you're defining. It could be not just boiling or melting point. So whatever you take here, corresponding low point, that is here, it should be the melting point, and HP is the higher point. Okay, so all of this should be equal, and that is what I'm going to use in the previous question, where x by 3, x is the new scale that he has defined. Okay, so here's the solution based on that. This is a general solution that was given in the textbook, right? But I think directly you can write that once you understood that linear slope. C minus 0 divided by 100 minus 0. Remember, the corresponding C for x naught by 2 has to be found. He himself gave that the 0, which is melting point, is x naught by 3, and 100, which is boiling point, was x naught. I think this gives you directly the value of C in one step. Instead of writing all this, you'll get that. Essentially, he did that, but it need not do this much. Okay, so direct answer for C. Let's move forward. Practice problem on another question from another exam, where a new scale, always he'll give low point, high point, and he'll ask you to solve for one of the variables in that slope form. Okay, so try it out. You should be able to match the answer. Calculations are a bit messy here. Should be able to manage. This is the solution. Let's move forward. Here's a practice problem which I'll answer in PHYSICSSIRJEE Quickies series. One important thing, when you have degrees R or degrees S or degrees U, these are actual exact value of the temperature at that point. Whereas when you have a quantity called R degree or S degree or U degree, degree are written after the letter, then they are considered to be difference in temperature in this particular problem. Okay, so these x1 and x2 and x3 that you are supposed to write in ascending or descending order mean the difference in temperatures on each of these RSU scales. RSU scales are defined in this manner. Okay, give it a try. It's a very simple JEE mains level question. Let's move forward. Slightly more difficult and challenging multi-conceptual problem, where I tried to club in a vernier calipers which is expanding upon heating. So this is thermal expansion plus vernier calipers, definitely at a JEE advanced level. Okay, so one or more than one is correct. Try to comment your answer below along with the timestamp so that I can go through it. Right. Next type of questions, right? So we are into calorimetry now, specific heats and molar heat capacities and all that. Okay, so we'll start with a basic question, where a bullet of mass 5 gram traveling with a speed of 210 meter per second strikes a fixed wooden target. One half of its kinetic energy is converted into heat in the bullet, while the other half is converted into heat in the wood. Okay, the rise of temperature of the bullet if the specific heat of its material is given in this form, and 1 calorie in form of ergs is given, and it is close to, again numbers look slightly disturbing. Okay, but I think you should be able to put up by now. You'd realize that out of 25 questions that you are approximately going to attempt in physics, 5 to 6 questions, please be prepared in your mind that they are going to be tough in calculation. So once your mindset is on that lines, you will not get irritated and you'll not waste time on them. Okay, right? You once you accept that kind of calculations are there, your positivity will take you through the exam. You're not bad in calculations. Indians are very good with our calculations. So try to accept that fact and try to not get frustrated in the exam. Okay, so let's move forward. Basic idea: half of that kinetic energy is lost to increasing the temperature of that wood. Okay, so half of half mv square is ms delta t. Always in such problems, read the question, account for the mechanical energy loss. Here it is kinetic energy. In another problem it could be potential or both. Then you'll end up getting the answer. Only thing you need to be very careful is this calculation. Okay, right. Let's take another problem of a similar kind. You could see the similar concept. They keep repeating. They like these kind of situations. Okay, so here instead of giving you some collisions and loss of Ke, he'll also talk about a loss of potential energy that is possible, or both. As I said, always account for the loss of mechanical energy. So go through this, try it out on your own, and match it with the answer that I'm going to show in the next slide. Right. So don't forget the two terms here. He's talking about the vessel and also water, both. So reading the question, container and the mass that is there, and also the water, not the container. Container doesn't have any issue here. It's the two objects that are receiving. So don't forget the two terms in the question. Half kx square is going to rise the temperature of both objects. Let's move forward. Another one of a similar kind. A metal ball of 0.1 kg is heated up to 500 degrees centigrade and dropped into a vessel of heat capacity 800 joule per Kelvin and containing 0.5 kg water. Initial temperature of water and vessel is this. What is the approximate percentage increment in the temperature of water? So straightforward, I think. Right. So this principle of calorimetry tells about the amount of heat loss is equal to heat gain. I don't like this equation when someone says heat lost or heat gained. Heat is not an entity that is a part of a system to gain or lose. Please understand that it's not like a path, state function. I know in our lower class textbooks we are told about this equation, but as you grow up, I think you should know the better language. The better way of writing principle of calorimetry is the sum of all flows of heat. Heat is a flow. It is an energy in transit. It is not something that is contained in an object. Okay, so instead of writing it this way as it is written in most of our textbooks, better written as sum of all q values with sign. Remember, when q is absorbed, we take positive sign. When q is released, we take a negative sign. So sum of all of them equal to 0 is a better way of writing. So write all these terms on one side and then write. So that would be a best way, right? So ms delta t1 plus ms delta t2. So on the other side, you just write it as final minus initial, 30 minus t. The sign will be taken care of for that. Okay, instead of writing it, especially people who are writing international Olympiads and all that, their presentation is also going to be important, and the person who is correcting your subjective paper will look into all these kind of things. Okay, so for objective papers it doesn't matter. Okay, so here's a question, slightly more multi-conceptual. You should have a decent knowledge of collisions of two objects when both are moving, and calorimetry, obviously. Right? I would expect 90% of you to be able to answer this very clearly. This can be either at JEE mains or JEE advanced level. Okay, so comment your answer along with the timestamp. Okay, right. Next one is the concept on water equivalent, right? So instead of giving specific heat of a material, they'll just call water equivalent. So you can think of replacing that object in your equation with equal amount of water. That's as simple as that. Okay, 500 grams of water and 100 grams of ice at 0 degrees centigrade are in a calorimeter where whose water equivalent is 40 grams. 10 grams of steam at 100 degrees centigrade is added to it. Then water in the calorimeter is, okay, so final amount of water, how much it stays behind is being asked. Okay, latent heat of ice and latent heat of steam are mentioned in the question. So you should realize whether this 10 grams of steam at 100 degrees centigrade is good enough to bring all of this to the other side of 100 or to the 100, or is it that this 10 grams of steam goes to this side? Okay, so that I think once you determine, then you can write the equation. Okay, so I tried my best to depict the same in a pictorial manner, even though the textbook does it very directly. So let's try to see what kind of variations the 10 grams of steam can do. Okay, so 10 gram of steam from 100 degrees centigrade, if it has to convert to 10 grams of water of 100 degrees centigrade, so this is a phase change. For any phase change, ml amount of heat will be released here in this problem. Okay, 5400 calories it gives out. From being a 10 gram of water at 100, it can change to 10 gram of water at 0. That means a temperature change. The formula utilized for heat released is ms delta t. When I plug in the values given in the question, I get 1000. So for the steam to become this 0 degree water completely, both combined, it will be able to release 6400 calories. Now, is this 6400 good enough for the ice to actually melt? If all the ice that was given has to be molten, then Q required is ml for the ice, which is in this problem 8000 requirement. You could see there is a mismatch, right? So with the 6400, only partial amount of the ice that was given will melt. So 1600 fraction of it over this 8000 will remain as ice. So all ice doesn't melt, only 80 grams does. Okay, I hope you understood how I got the 80 grams here. Okay, so the ratio of these energies that I have here. Okay, so therefore the here water equivalent is not important, because the water equivalent that is available in this particular problem would have been required only if the equations were written for the temperature changes to beyond the steam. Okay, so for example, imagine this was, let's say, 140 degrees centigrade steam. This entire stuff goes to other side of 100. Then the calorimeter's water equivalent will not be converted to steam. Remember, it stays as water equivalent only. So a lot of students, they make a mistake in that new problem of taking 540 grams of water. Here it is okay. By taking 500 plus 40 grams, since you are not changing the phase of this water, here this important, this particular value was not of any trick. Okay, right? I'll try to give you another idea of a question where your water equivalent can be used by the examiner to trick you into doing a mistake. Okay, right? Here this 500 grams of water stays where it is, that is 0. Only these two are interacting. 100 grams of ice, so 80 grams of ice has molten, so 80 grams of water is formed. So total is 500 plus 80 of this plus all this 10 grams, so answer is 590. Okay, easier problems with final state mentioned. So principle of calorimetry, there are two types of problems I have easily noticed, and most of times they tell you the final state. Okay, right? You could see when m1 grams of ice at minus 10 degrees centigrade is added to m2 grams of water at 50 degrees centigrade, finally no ice is left and the water is at 0 degrees. He has given the information already. So don't run away from such questions. Always try to surf through the question completely and see if the final state is mentioned. That's a pretty easy question. He's already telling you what should be written on the left hand side of the calorimetry equation and right hand side. You need not investigate where that final temperature is, unlike the previous problem. In the previous problem, I didn't know what is a final state. I had to investigate it. Like, this is a longer looking problem. So if you're smart, you look for this. Okay, so I think once that is mentioned, it's a direct equation step. No need to investigate the way I did. You'll get the answer in one quick go. Okay, right? You could see many times these are repeated. Just I'm giving you one more practice problem. You could see here also the final state is already mentioned. So pretty straightforward. Okay, I hope you have matched your solution. Let's move forward again. Another one with slightly difficult calculation. So this was the latest paper, September 4th, 2020, as you could see. Again, but it's a boring little question. Only he was interested in calculation. Numbers are very close, as you could see. Okay, right? But the question concept wise is a very simple one. Once he says final temperature is given, I think it's a easy problem to jump upon. Match the solution and we'll forward. Okay, let's move forward. Another one. Let's search for that. Calorimeter. This is slightly different. Okay, a calorimeter of water equivalent 20 grams contains 180 grams of water at 25 degrees centigrade, m grams of steam at 100 degrees centigrade. Again, 100 degrees centigrade is boring, right? So, right, 20 grams and this 180 grams of water, you could combine it to be a 200 grams of water is mixed in it till the temperature of mixture is 31 degrees. I told you, right? Well, they are making very easy questions, right? So this is of not much use. It is useful in the calculation, but it won't be anything tricky. Final temperature is given. You can just go ahead and write the equations. Easy here. I've taken already 180 plus 20 together as 200 grams of water. Okay, as I highlight, you can't do this equivalence once the steam, let's say, was 140 degrees centigrade and temperature of the mixture is found to be greater than 100 degrees centigrade. Imagine temperature of the mixture, let's say finally is at 120. Then how do you investigate this? You would say that water 180 degrees actually went through the phase change and not this 20 grams. This 20 grams calorimeter stays like the 20 grams with specific heat of 1 and you take it to that 120 degrees. So you have to write this one separately in that problem, and 180 grams you have to write for both ms delta t and ml. You will not write this 20 grams into ml. That's what I'm trying to tell. Till now they have not given a question on that concept, but I think they will if they are interested in. Okay, so please keep your eyes open for this right side caution that I am trying to point to. Okay, I hope you understood what I said. Let's move forward. So here's a practice problem for a tricky question on water equivalent. There's no phase change in this, as I promised. Phase change question I have not made, but this is a question that you can think of. You could see, let me read it out for you. I'll give you a solution now itself, okay? So that you understand what I was trying to involve upon. 2 kg water at 100 degrees centigrade and 2.5 kg water at 50 degrees centigrade is kept in two identical containers A and B respectively of water equivalent 0.5 kg. So containers water equivalent is 0.5 kg. In two independent experiments, if water of container A is poured into container B, the final temperature of the mixture is T1. And in another experiment, if the water of container B is poured into container A, the final temperature is T2 and heat loss is negligible. That means whatever contents you are pouring into that container, the container plus the water together, the calorimetry principle is valid. That is what heat loss is negligible means, that Q1 plus Q2 plus Q3 is equal to 0. Mark the correct options. Okay, more than one may be correct. So please do give it maybe 1 or 2 minutes. It's at the JEE advanced level. Can still have it at JEE mains level also. There's nothing wrong in it. Papers have given slightly tougher questions in the last two exams, especially if you're attempting this in a later shift, right? The shifts as you move from February to March, March to April, right? Later shift question papers should be usually tougher than the earlier shifts. So here's the solution for it. Pretty straightforward. This is the first case. I have demarcated the cases separately. Can you see? That's the first experiment and this is the second experiment. I've just again written ms delta t of both. In the first case, the 500 grams, that is 0.5 kg is added to the whatever vessel into which it is being added, and rearranging, you would get T1 is 70. Whereas in the second case, the 2.5 kg water at 50 degrees is mixed with 2.2 kg of water. So this time you end up having here the 500 being added on this side. Obviously T1 won't be equal to T2 and T1 and T2 values would be different. If water equivalent was not given and you are not mentioning, I think you realize that these two experiments would have yielded the same answer. Because of the presence of the water equivalent, the answers are different. Okay, should be able to appreciate the presence of the container also in the calorimetry equation. Okay, right, let's move forward. Water of volume 2 liter in a closed container is heated with a coil of 1 kilowatt, some power related situation. While water is heated, the container loses energy at a rate of 160 joule per second. In how much time will the temperature of water rise from 27 degrees to 77 degrees? Specific heat of water is this much and that of the container is negligible. Okay, so the entire system is actually losing heat. So whatever 1 kilowatt that you're supplying, all of it is not going to heat the water. This looks like a time calculation, but it's very simple actually once you understand that it is a constant power. Okay, I hope you have tried it. Here we go with the solution. So don't forget to subtract whatever is being lost. Okay, so 1000 joule per second, which is kilowatt, is being delivered, but only 840 is being used by that water. So ms delta T that you are using, if you can calculate, the value of that should be equal to power into time. Remember, ms delta T is the joules and 840 joules per second is being supplied. Therefore, amount of time should be simply that ms delta T divided by the power that is useful power, not the wasted one. You'll end up getting 8 minutes 20 seconds. Pretty straightforward. Don't forget to just subtract it. Reading the question is one of the most important things in JEE mains, especially with questions being easy, they'll try to manipulate the language. Okay, so don't fall for it. Stay confident. I think you should do better. Let's move forward. This one again, I just put it up here to tell you that question might look big, but the solution is very, very simple. Okay, right. So don't go by the face value of the question. Give it a try. Just read it, process it, and if it then looks tough and lengthy, then only leave the question in the exam. Okay, never waste time. You just give it a 45 seconds to 1 minute, and you don't get it, you go to the next one. But once you don't read it and you just label the question as tough one, then it is not a correct approach. Okay, so I'll just provide the solution in the next page. Solution looks very long. It's actually not. The textbook has tried to print a lot of steps. If you're a decent student, I don't think this many steps are required. So try it out and just pasted this one so that you can match your answer. Okay, right. Let's move forward. So for those who are craving for a slightly difficult question, okay, so here it is for a three-phase mixture, right? This is slightly at a JEE advanced level. So ice and water and steam, all three are mixed. All three specific heats are mentioned. And I would like you to provide me with more than one correct answer about the options that are given. Not very tough, but definitely a good practice for calorimetry type of questions. Okay, so I'll provide the solution in ATS select series. You may comment your answer. I'll try to correct it or let you know whether you have done it perfectly or not. Okay, so let's move forward. Here's another one on flow calorimeter. This is definitely slightly tougher than the previous problem. So the same procedure, try it out for 2 or 3 minutes. Read the question carefully, try to manipulate all the numbers that are parameters that are given, how they can be interrelated, and this is slightly multi-conceptual, you could say. Okay, you should be able to crack it. It's not very difficult. Any calorimetry question, you should be able to. Thermal properties of matter, they might give you multiple concepts, but it all be related to energy conservation. Okay, so I'll be waiting for your answer in the comments. This time I mixed a concept of thermal expansion with calorimetry. You could see, right? We are coming to the end of calorimetry. So thermal expansion is already done. So you can have at a JEE advanced level, or even the numerical value questions, if they tend to become tougher in JEE mains, you can expect this kind of a level of a question, right? So it's not just about reading it, how quickly you can solve this question is very important. So have the patience, read it properly, give it a 1 or 2 minutes try, just comment your answer below. Okay, it's an integer based or a numerical value based question. So let's move forward. Another one for your practice. This is related to the phase change ideology. Very standard one from JEE Advanced. Not many times have been asked in JEE Mains, but there is a very good chance of this kind of questions being copied from JEE Advanced to JEE Mains. There have been instances where JEE Advanced previous paper questions have come in JEE Mains. Okay, so expecting this type of questions also to make an appearance. So here we move forward. Another one. This is definitely at the Olympiad level. Okay, so or higher level of JEE Advanced. So I'll explain this very clearly. This is a case where specific heat is varying with temperature. Usually MS delta T is an ideology that we use when specific heat is remaining constant with temperature. So I've taken two substances and mixed them whose temperature variance of specific heat is given. Okay, so substance A, specific heat versus temperature from T0 to 2T0 is this way, this red line. Okay, whereas substance B's having a specific heat which is decreasing with temperature. Both are linear increase and decrease, and angles of their slopes are also given, as you could see. And not very straightforward question for sure. Okay, so I would be eagerly waiting how many of you can solve and give me the answer. I'll definitely come up with the solution of this first, because this is tougher question in the AITS select series. Okay, so put your comments and the answers. Okay. This is a very important, generally left out concept, because I would say in NCERT physics textbook, this concept is not there, but in the exemplar questions, they have mentioned the concept of supercooling of water. Okay, so here, because of the length of the video, I cannot take it up. So I'll be answering this as quickly as possible within 1 week time. In NCERT physics in-depth doubts, I have already have a series on that. There are 3-4 questions I have already answered in that series. You can check it out. So in that series, I'll be answering this one. Okay, so by the time this video is uploaded within few days, that solution would be put up. This is a very important problem about supercooling of water. There is a concept of idea that whenever water is supercooled, that means instead of um, becoming frozen at so-called temperature of -10 degrees, it still stays as the liquid state. Okay, so one small agitation or perturbation or a disturbance that can be created inside it, it causes a part of that water to freeze. There are super cool videos on YouTube. So just type super cooling of water in YouTube and you will see all kinds of nice videos and explanations in that concept, and just watch them, but also wait for the physics solution that I'm going to provide for this. Okay, so try it out. Some of you might be knowing this who have solved NCERT exemplar problems. It's in the subjective part of NCERT exemplar. Okay, right, let's move forward. For those who are interested in the IOQs, slightly tougher concepts on supercooling and superheating. Opposite of supercooling is superheating, where it happens in pressure cookers. You try to increase the boiling point by applying pressure and decrease the melting point by applying pressure. Okay, so remember the concept of regelation. So these are the two problems in Builder Your Understanding in Pathfinder, where you, once your concept is very clear from the previous two problems, I think you should be able to attempt this and ace these problems also. Give it a try. I'll come up with definitely the solutions of these concepts in Pathfinder solution series. Okay, right. A specific heat, now we are entering situations where the heat capacities could be functions of temperature. So what did JEE mains people ask on this? The specific heat capacity of a metal at low temperature T is given as this number. Okay, a 100-gram vessel of this metal is to be cooled from 20 Kelvin to 4 Kelvin by a special refrigerator operating at room temperature of 27 degrees centigrade. The amount of work required to cool the vessel is given some ranges and values. Okay, try to read the question. There are quite a few things that are going here. 3-4 temperatures are given. So try to work out what is happening, what equation you are supposed to write. Okay. So I hope you have done that. Let's move forward. So the idea is very simple. The amount of work that is required, he asked, should be equal to energy released, right? That means I'm talking about Q being equal to W because delta U is 0. And how do I know that? Remember, he said refrigerator is working at a constant temperature of 27 degrees, and this 27 degrees is not needed. What is needed is the idea that it is at a constant temperature. So delta U being 0, the Q supplied is only used for the W. That is work to be done on it. Okay, right. I've used first law of thermodynamics. So it's actually a multi-conceptual question on the first law included into the thermometry. Okay, so not thermometry, calorimetry. So integral of ms delta t or mc delta t, right, where it's a function of temperature is given, and your change in degree centigrade, that Kelvin, actually he has mentioned it in Kelvin, is to be taken, and then you end up getting the required value of the work. So exact value of 0.002 kilojoules. Okay, let's move forward. This is slightly an offbeat problem that appeared in April 22, 2013, where you could see in the previous problem, why I'm giving that as a practice problem, you could see this ideology being utilized in the next problem also, but delta U need not be 0. Similar question is also there in HC Verma and been asked in JEE Advanced, where melting of ice as a process in an open system, you could realize Q, delta U and W, all three concepts will be there. It won't be 0 like in this problem, which is what happens in this particular situation. So I've already given you the hint enough to solve the question. Try to look at the options, try to apply your first law, and I think you should be able to comment your approach. I'll give you the answer also so that you can check it carefully. I'll not give the solution, but you can comment the approach by marking the timestamp in your comment section below so that I can check your approach there and reply in case you are not doing it correctly. Okay, this should be a cakewalk now that I have given the hint. So let's move forward. We are into heat transfer. So we'll start with conduction. We'll move on to convection and finally the radiation concepts. Okay, so 3 rods of identical cross section and lengths are made of 3 different materials of thermal conductivity K1, K2 and K3 respectively. They are joined together at their ends to make a long rod like this one in series. One end of the long rod is maintained at 100 degrees centigrade here, and other end is maintained at 0 degrees centigrade. If the joints of the rod are at 70 degrees centigrade and 20 degrees centigrade in steady state, and there is no loss of energy from the surface of the rod, that means there is no radiation losses, find the correct relationship between K1, K2 and K3. Very standard form of asking questions. You will see in the next few slides how many number of times this type of question has been repeated. So most of you should be able to ace through. So I'll just quickly go through the concept that is required. This is the usual solution, right? I think you'll be able to go through it on your own. So the equivalent solution is to consider that these are situations similar to the Ohm's law from current electricity, where thermal resistance in this chapter is related to L by Ka. There you'll write rho L by A if you remember, resistivity on the top. Here K, which is thermal conductivity, is written. So in this chapter, R is thermal resistance, K is the thermal conductivity. Okay, and V is equal to IR of that chapter, delta V, which is the potential difference, is replaced with temperature difference. I is the current here, which is power, heat current, right? Joules per second, and R is the thermal resistance. So whatever formula you had learned and whatever symmetry and concepts that you have learned in Ohm's law resistances, you should be able to put forward in this chapter also. Okay, so R1 and R2 and R3 are mentioned in the question. If this is 100 and this is 0, is already said this is 70 and 20, the temperature differences are directly proportional to resistance, because in series the heat current would be the same. So the differences are, you could see 100 minus 70 is 30, 70 minus 20 is 50 and 20 minus 0 is 20. Therefore delta theta should be proportional to R, and R is inversely proportional to K for same length and A. He already told you that they are having same length and A, therefore delta theta is inversely proportional to K. So the case ratio are 1 by 30 is to 1 by 50 is to 1 by 20, which directly gives you this step, which is what he has done. But I think visualizing it in this right side diagrammatic manner will ensure your problem solving is quicker. Okay, right. And you could see, you can practice this in another problem. Series connection, again, they give you every information. This time lengths are different, as you could see. Please be careful with your thermal resistance calculation, and you should be able to ace through this problem very easily. Okay, so here's a solution for your cross verification of your key. Okay, I hope you have got it correct. So let's move forward. Another one in 2007. I think this is even more simpler. Okay, so he's given everything in parameters. Okay, so try this one out. More interested, if parameters are given, I think you should be smarter and sharper enough to save time, not do all this. Okay, obviously for numericals you have to do, but for parameters, where you can substitute some boundary conditions and check the answer, right? Right. So instead of doing this and waste time, can you think of an educative guess among the four options by putting some boundary conditions? I would be eager to know what kind of boundary condition and guesswork will you do to save time and mark the option clearly. Okay, so we all know if you go about honest method, you'll get this answer. But is there a way to select this answer without solving by just substituting some interesting values for these parameters? So just comment below. Now we are into the graphs part of the conduction, steady state conduction ideas. Okay, so a long metallic bar is carrying heat from one of its end to the other end under steady state. Our syllabus only has steady state conduction. Okay, so that means that temperature of any slice doesn't vary with time. Over a period of time, temperature remains same is the definition of steady state. The variation of temperature theta along the length x of the bar from its hot end is best described by which of the following figures. So it's asking you whether it's a straight line, whether it's a curve, then which kind of a curve. From one end, hot end to the cold end. Okay. I think from hot end to cold end, it should be a decreasing function. So it can definitely not be option D. Our job is to judge between A, B, C. That at least you should have guessed it. So the idea is to write that heat conduction law where dq by dt is the heat current. Remember, heat current is not amperes. Electric current is amperes. Heat current is joule per second, which is watt. Okay, so dq by dt is Ka delta theta divided by delta x, which in this problem is x itself because origin is taken on the left side. Okay, so the value of the delta theta can be written this way, and you will have y is equal to mx plus c type of an equation. Y is equal to m is this entire number. Remember, dq by dt is a constant in a single rod, right? Whatever enters should leave. So this is plus c. This is a pretty simple straight line with a negative slope. So you should have selected the option A. Okay, let's move forward and check another slightly more challenging graph. This time I have two objects in series. Then what kind of a temperature profile will you get? Obviously, two different slopes. Okay, so this is definitely at a JEE mains or a JEE advanced level. It's more about your ability to manipulate these numbers to get to the answer quickly. Okay, so comment your answer below along with the timestamp. I'll give you the solution in AITS select series. Let's move forward. This time look into the cylinders being surrounded by another cylindrical shell. So this is parallel type of connections that are also asked quite often in JEE mains examinations. A cylinder of radius r is surrounded by a cylindrical shell of inner radius r and outer radius 2r. The thermal conductivity of material of the inner cylinder is K1 and that of the outer cylinder is K2. Assuming no loss of heat, the effective thermal conductivity of the system for the heat flowing along the length of the cylinder is pretty straightforward parallel connection. Okay, so let's not waste any time. So if one rod surrounds another one and you're heating it from one side and extracting the heat from other side, and the temperature difference between the two ends, as you could see I'm pointing out, would be equal to each other. Okay, so that's a nice case of a parallel circuit. So the heat current will divide in the inverse ratio of their thermal resistances. So I've drawn an equivalent Ohm's law type of a circuit where heat current enters and leaves from here. This blue color rod that you have is depicted by this blue thermal resistance, and red one is depicted by this. This is the straight on view or the axial view, right, which is of not much importance. This is enough for your solving. So 1 by R effective thermal resistance should be 1 by R1 plus 1 by R2. So rearranging, you should get K equivalent. Remember, the K equivalent would be on the top here, should be equal to the K1 A1 plus K2 A2 divided by A1 plus A2. Straightforward. Don't forget A2 is not 4 pi R square, it is 3 pi R square. You should be able to close the matter. Straightforward. Let's move forward. Series parallel combination questions, right? Again, this is pure Ohm's law type of solution. So I think you should be able to read this question on your own and apply the concept. So from A to B, if the heat is flowing and you've made a bridge kind of thing, you should be able to say this is a resistor, this is a resistor, this is a resistor, and complete the circuit, use your series and parallel ideologies, you should be able to get the answer. Okay, so here's a solution for that. Use R is L by Ka and write all these resistance in terms of Rs. Okay. right? Pretty straightforward. Delta V by R of Ohm's law becomes a delta T by R for the heat current. Okay. So another one. Then they start giving questions which are slightly more complicated in terms of series parallel, right? This is one of the old questions where they gave a Y junction. Okay, again you'll be able to use in Ohm's law type of problems KCL and KVL. You can utilize the same ideas even in conducting rods. Okay, so I'll quickly go through this question. I'll not read the entire thing. There is a Y-shaped structure. Three materials are making a Y junction, and the end of copper is maintained at 100, whereas the ends of brass and steel are maintained at 0. Lengths will be given. All the important informations for thermal resistance will be given. The K is given, L is given, and area of cross sections are mentioned to be here. Okay, so L, K, and A. So L by K is known. So rate of heat flow through one of the rods is how much? Okay, copper rod is being mentioned. You should have attacked this question immediately. The length of the question is slightly long, but it's definitely doable. So this is the Y junction that we have drawn. So this is equivalent to using Kirchhoff's current law, that is sum of all the currents leaving or entering a section or a joint or a junction as it is called should be 0. So just Q dot is the dq by dt that I have written here, which is Ka delta T by L. So copper is equal to brass plus steel, direct application of the formula, and T is the junction value. We should be able to get T. Substitute the T equal to 40 back in this by using 100 minus 40 here and copper, we should get 4.8 calorie per second. Okay, right, slightly lengthy in calculation, but 2 steps maximum. Let's move forward. I have made a better question. This is related to the Wheatstone bridge idea that we are pretty much used to in the current electricity chapter. So I've tried to apply it to the heat conducting situations, but this is more of a theoretical type. Instead of giving you numbers and you will easily solve the problem, I've tried to ask something more theoretical and intuitive, and one or more than one may be correct in this. So please do comment your answer along with the timestamp. Okay, so let's move forward. Now, spherical or radial heat flow of substances. So let's try to see this. It's from very old paper, but has been asked quite a few number of times in the recent times also. So a figure shows a system of two concentric spheres of radii R1 and R2 are kept at temperatures T1 and T2 respectively. That means inner part is T1 and outer part is T2. So the heat is going to flow radially outward this time, not along the axis like in the previous problem. So the radial rate of heat flow in a substance between the two concentric spheres is proportional to which of these numbers? Proportional to. So he doesn't want the entire calculation. Which of these terms will appear in the final integration? Okay. So I hope you have given it a try. Let's move forward. Right. So if the heat is flowing, can you see on the left hand side in the radial manner, all these layers can be considered to be having the same dq by dt. Whatever enters should leave in steady state. So that's what I have written here. As you could see, dq by dt across all the spherical layers would be same. All right, and we can call all the layers to be in series. Okay, so when you write for this differential layer, which is from R to R plus dr, the value of dq by dt should be related to Ka, temperature change across this is dt, divided by length across the change is dr. Remember, length this time is along the radial direction. That's why you have a dr here. And what is the area of that section that it crosses? Remember, you're supposed to visualize that the area is radially touching. Okay, so that should be 4 pi r square. That's what he has written. So dq by dt, you should directly be able to write this step. Okay, and in all of this, please understand dq by dt is not dependent on radius r. So you go to the another radius also, this dq by dt is like a constant. Let's call this a c in your mind. So when you rearrange this by taking drs and rs on this side, and c will come out of the integration, and on the right hand side you will be left with 4 pi k dt with a t1 to t2 integration. So when you integrate it from the inner radius to outer radius and inner temperature to outer temperature, dq by dt will be just standing here clapping. Okay, it will not be a part of your solution. That's why it's a proportionality constant. Just because there is a dt, don't try to fit into the integration. You are integrating over space and not time. Okay, so therefore the value of the heat rate or heat current, as it is called, is proportional to therefore R1 R2 by R2 minus R1. You won't get a logarithm in this type of a variation. In cylindrical variation, where you'll have a 1 by R, you'll end up getting a logarithm. Okay, right. Let's move forward. This is a practice problem on that spherical shell variation. Only difference I have made here is that thermal conductivity K, which in the previous problem of JEE mains was a constant. Here I have made the thermal conductivity a variable with space. Okay, so there's one or more than one correct isothermal surfaces and all that. Try to attempt it. This is very straightforward question, but you need to be very good with your calculations. Okay, so read it and comment your answer along with the timestamp, or wait for me to provide the solution in the AITS select series. Let's move forward. Now we have entered radiation chapter. In radiation also subtopics are there, where we'll start off with Stefan's law, then we will move on to the other laws like Kirchhoff's law and Newton's law and Wien's law. Okay, so here it is. The heat radiated per unit area in 1 hour by a furnace whose temperature is 3000 Kelvin is the value of sigma, which is nothing but Stefan's constant is mentioned. Pretty straightforward. He's just checking whether you know the Stefan's law formula or not. I think this is the solution that you all should agree to. Okay. Heat radiated per unit area in 1 hour. So this is called emissive power. Emissive power. Okay, so the emissive power is sigma into T power 4. Emissive power is watt per meter square. It's an intensity. Emissive power is an intensity. Okay, and 1 hour you should convert it to 3600 seconds and you should be able to write this thing. Okay, joules. Let's move forward. Next, it's a question on idea of solar constants. Again, 1 or 2 times it has been repeated, and it's a very good candidate even for the JEE advanced questions. Okay, assuming the sun to be a spherical body of radius r at a temperature of T Kelvin, evaluate the total radiant power incident on Earth at a distance r from sun. Okay, so is based on solar constant, which is related to the amount of energy received by Earth per unit area per unit time from sun. Okay, so the word is not used here, but what he's asking is related to that. Okay, so I have just drawn a crude diagram of sun and earth here on the right hand side. Please watch here. So this is the sun of radius capital R, and earth, which is blue in color here, is at a distance small r. Assume the sun is radiating out heat in spherically all directions uniformly, and I can think of it as having a power wavefront. Okay, heat wavefront of radius 4 pi r square by the time it reaches the earth. Earth is considered to be very small in size, so you can consider this to be a point mass in the scale of this r. Okay, right. So whatever power that you have from earth, sun, which is coming out from its surface, is given by Stefan's law this way, right? Sigma area of the surface of sun, which is 4 pi r square, into T power 4. This power will be spread on this wavefront and keeps expanding. So its intensity as it expands reduces. So what is the intensity of this power as it reaches this yellow wavefront position? Obviously, it is power per unit area of the wavefront. So you have to divide this 4 pi r square with this entire term. Don't cancel capital R and small r. Okay, so that's what can you see he has done. Okay, and that's what is the required answer. So the total power received by the earth would be this number multiplied by whatever is the cross-sectional area, which is the projection area. Remember, only one side of earth is going to receive. So that's why this number you could see is related to pi r naught square. What is r naught? R naught is the radius of earth. Okay, so that's the idea. I hope you understood it and appreciate it. So in case you do, just practice this problem on a similar concept which was asked in 2004 past paper. Similar. Okay, right. And match your answer in the next slide like this. Draw the diagram. It would be much easier to analyze when you label the radius R1, R2, all these things. It could be quite confusing. What is the radius of the earth? What is the radius of sun? And what is the radius distance between them? Please be very, very careful. Okay, right. Now there's a question with radiation combined with calorimetry, a multi-conceptual one. Okay, so let's have a go at it. This is one of the tougher questions among the radiation chapter that I have seen. A black colored solid sphere of radius capital R and mass capital M is inside a cavity with vacuum inside. Oh, the walls of the cavity are maintained at temperature T naught. The initial temperature of the sphere is 3 T naught. If the specific heat of the material of the sphere varies as alpha T cube per unit mass with the temperature T of the sphere, where alpha is a constant, then the time taken for the sphere to cool down to temperature 2 T naught will be sigma is the Boltzmann constant. So this is a nice case where calorimetry also is giving specific heat variable with temperature and is also involving some ideas about the radiation or Stefan's law. Okay, I hope you are excited to look through the solution of this after giving it a fair try. So let's move forward. This is slightly on the difficult side. So for JEE mains level, I would say this is one of the tougher questions which involved integration by substitution actually. And please do remember, here you cannot use Newton's law of cooling, which I'll cover in the next slides. When is the concept of Newton's law of cooling? Just give you a tidbit here. Newton's law of cooling is applicable only if the temperature of the body and surrounding are very close to each other. That means the difference is very small. Here you could see the differences that you are talking about are large enough. 3 T naught and T naught, it's large enough that you cannot use a linear law. You have to use the Stefan's law with power 4. So the value of the d theta by dt, that is rate of change of temperature, is given by sigma into area into emissivity into this temperature difference divided by ms. Remember this dq by dt, I could have written as ms delta t by delta t or dt by dt. I brought the ms down. Okay, so this upper numerator is the Stefan's law term. Okay, so this makes it a very difficult integration to bring this d theta on thetas on one side, because power 4 is a very difficult integration. He made it simple by giving the specific heat as a function of theta cube. So there is the magic here. If you are patient enough not to worry in the exam, you would have got this. So this theta cube goes onto that side, brings this theta power 4, gives you a nice integration by substitution. Can you see? If theta power 4 is substituted as some, or denominator is substituted as some x, this numerator entirely is the dx. Can you see that? Makes it a very easy integration. Would have been actually difficult if the specific heat was not given as function of temperature power cube. Okay, so then this will come out of the integration and you would have been stuck with a very tough, doable, but very tough integration of power 4. Okay, so I think you'll appreciate this and then be able to substitute the values and get the time. So in terms of the length and the patience required for attempting this question, this is definitely tougher for a usual JEE mains level. Don't expect all questions to be of this level and get demotivated, I think, but you should keep your eyes open. If you are aiming for a better rank, these kind of questions will cause a difference in the ranks. Okay, so here we move forward. So now let's move into Newton's law of cooling, and we'll start off with the graph type of questions. I've pasted both the problems in the same page to tell you the similarities in way they are generally asked in the exam. So let's read the left side one. If a piece of metal is heated to a temperature theta and then allowed to cool in a room, which is, whenever the word room is used, please understand difference is very small. Whenever the word furnace is used, like in the previous problem, then the temperature difference is large and you can't use Newton's law of cooling. Newton's law of cooling valid only when the difference is small. Usually our day-to-day life activities where you have an object in a room or a coffee in a room, these kind of things you can use. The graph between the temperature T of the metal and time small t will be closest to 2. Okay, so as the metal is going to cool down, the temperature of the metal versus time, which of these graphs is the best way of representing it? Same thing in logarithmic graph. So why I clubbed these two is both are similar logics, and here temperature is asked, here log of temperature is asked, the beaker, surroundings and all that. So please attempt any one of these or both and then move forward for the solution that I'm going to present. So here it is. So for this first one and the second one, 63rd one, you should so look at this second one, right? So when you write d theta by dt is minus k times of theta minus theta naught. So this is your Newton's law of cooling equation, wherein the power 4 of your Stefan's law is no longer considered. You just consider the linear variation, right? And please, you should realize that Newton's law of cooling is not just a radiation idea. It will involve even convection also. Okay, so this is a law and it's not derived from Stefan's law as is depicted in some textbooks. It is not always a derivation from Stefan's law. It is a combination of actually radiation and also convection. So law is something that is experimentally found out. So experimentally this has been proven in the case of these kind of situations. Okay, so this is k is a constant, and you bring this theta minus theta naught, and this time this is much more easily integratable as compared to the previous one, and you'll get a logarithm. So that's why log versus theta graph is a straight line, but whereas the temperature versus this should be an exponentially decaying function, and that's why you end up getting the solution as required. Okay, so here I think now you're good enough to be able to attempt questions on graphs on Newton's law of cooling. So here is my spin of the problem to highlight the point that the constant K is actually not related to only the radiation part. It will contain even the convection idea. Okay, so you need conceptual clarity to answer this theoretical question. So please do mention one or more than one may be correct. Try to answer it in the comments below. I'll come up with the solution of this in the PHYSICSSIRJEE quickies very quickly. Okay, right. So I've seen a lot of students make a mistake on this. Okay, so let's see how many of you get it right in the comment section. Next one, practice problem with log calculations. Okay, so the Newton's laws of cooling, whenever logarithms are mentioned, and you'll clearly see once the log values are mentioned and the answers are very, very close to each other or decimal form, then you should be able to remember you derived a form, right? This one, let's go back. This one, this is the form we are going to use. That means this is the graph or this straight line graph in log we are going to use. Okay, a hot body obeying Newton's law of cooling is cooling down from a peak value of 80 to an ambient temperature. What's ambient temperature? Ambient temperature means surrounding temperature. Okay, of 30 degrees centigrade. It takes 5 minutes in cooling down from 80 degrees centigrade to 40 degrees centigrade. How much time will it take to cool down from 62 degrees centigrade to 32 degrees centigrade? Okay, so this is the information given. Pretty straightforward once you know the derivation. Don't mug up the formula. I think you should remember minus d theta by dt is equal to k times of theta minus theta naught. And once you quickly derive, don't remember, this fellow just wrote it directly from the textbook. I have taken the solution. So you can do the derivation in the exam very quickly like this. This is something that you should remember. Very straightforward, right? D theta by dt is minus k times of this. Bring this one down, integrate, and you write this. This step, he wrote it directly here by converting it to t equal to, and substitute the given information given, divide logarithm values that are given, that you substitute, you get the answer. Definitely 1 or 2 questions will come on this in on each day of your February shifts. Okay, so practice more on this. Now we are going into even a better way of solving the Newton's law of cooling, easiest way I would say. So when furnace is used, you have to use power 4 law, and Newton's law of cooling is there, logs will come, but within that log you can make it further approximation that it can be a straight line graph. Okay, so how do you know that? If the answers given are not in decimals and they're far away from each other, you can actually make this logarithmic function or the graph that we saw, right, that curve, you can make it into parts of straight lines. So let's try to see how it can be done. It's a standard method, standard problem, a lot of you know it, but you need to know how quickly you can apply it. Hot water cools from 60 to 50 in first 10 minutes and to 42 degrees centigrade in the next 10 minutes. The temperature of the surroundings under whatever ambience it is there is how much. So let's try to see what is this approximate idea, also known as straight line fit approximation. So what they generally do is your actual curve, that t versus t, which is actually exponentially decaying, when you are given some temperature changes, you can, without much error, assume that if, let's suppose, look at this, the top one, you can say from here to here, 2 points I have marked here, you can, instead of saying that it goes along a curve, you can take it as a straight line, like a chord. That's called a straight line fit approximation. Okay, this fit is better and better if these two are closer and closer. So compare to another fit from here to here. I think the first line that I have drawn is much better approximation as compared to the second line. So your straight line fit will have an error, but error becomes smaller and smaller if the 2 points on the curve that you're taking are closer to each other. Then instead of writing this and integrating, you can directly say the slope of the straight line that I have written, or the chord that I have written here, can be written as final temperature minus initial temperature by time taken. Straight line, right? Y2 minus Y1 by delta T. That's what I've written here. And what should I write for theta? Actually, theta is varying, right? So, but I have to write only one value here. So the best value is the average value. That is the arithmetic mean, the exact middle temperature. So if that object is changing its temperature from 60 to 50, right, 60 to 50, then average value of this is 55. That 55 goes onto the right side, whereas on the left side the difference of 60 and 50 goes. So you could see he has written the same. 60 minus 50 by 10 is equal to k times of 60 plus 50 by 2 minus this thing. Theta naught is the surrounding temperature. So he has given for two parts, right? 60 to 50 and 50 to 42. Never take directly from 60 to 42. Don't take this one and use 20 minutes. Don't do this. Okay. If you do that, error will be higher. You could see, instead of taking two parts like this, can you see the way I have written in the diagram on the right side top? If you directly go, you're farther away from the graph. Okay. So a straight line fit is a better fit once you divide the observation periods into much smaller periods. So if then another student does this experiment in parts of 5 minutes, he will get more accurate values as compared to the person who is doing it for 10 minutes each. Okay, so that could be a theoretical question to check your understanding of the straight line fit approximation, quite often used in JEE mains exam. Log problems are lesser asked, straight line fits are more asked. And you could see, as I have given some practice problems for you, apply the straight line fit for this one, try to get the answer. You see no logarithms mentioned, all the numbers are integers and farther away, happily go ahead and apply the straight line fit. Practice properly, you should be able to get these marks. Okay, so you could see the solution, match it out with you. You could see the answer is not exactly that, so it's close to also. They don't mention close to. He said approximately, so that should be a key to applying straight line fit. Okay, another from latest exam to prove my point that they keep asking these questions. There are many more actually in the September shifts. I picked just one so that the length of the video doesn't go very high. Okay, so I picked one of them. That's it, randomly. Try it out. Reading the question. Okay, so he said next 5 minutes. Okay, so here's the solution. Here is your straight line fit formula. You should be able to get it, right? Let's see this one. Okay, so April 2019, two identical beakers A and B contain equal volumes of two different liquids at 60 degrees centigrade each and left to cool down. Liquid in A has density of 8 into 10 power 2 kg per meter cube and specific heat of 2000 joule per kg per Kelvin. While liquid in B has a density of 10 cube kg per meter cube and specific heat of 4000 joule per kg per Kelvin. Which of the following best describes their temperature versus time graph schematically? Schematically means he's not worried about the curve, it's just worried about the intersections, who lies above each other and all. Assume emissivity of both the beakers to be the same. Okay, right. I think you should be able to do this very easily. Try it out with confidence just for 30-40 seconds. And here we go. So rate of heat loss is dq by dt is not rate of cooling. That's what I wanted to highlight in this problem. A lot of people, whenever they say rate of heat loss, they try to think, or rate of cooling, they try to think it is dq by dt. Rate of cooling, the word rate of cooling means rate of change of temperature. So what's the units of rate of cooling? Kelvin per second. What is rate of heat loss? Joule per second. Don't mismatch the two. Because when they ask the ratios, or when they ask this greater or lesser, the ms delta t by delta t is different from delta t by delta t. Okay, right? And you could see it's just use the Stefan's law. There's no way you can use here again directly the idea of Newton's law of cooling. Okay, so there's no requirement here. Okay, all right. That's why T power 4 was used. It gets cancelled anyway. So it's more about the density part. So even if you have to use Newton's law of cooling, the power for both the objects would be same and they will get cancelled. Okay, so it's more about this number. I think you should And remember, cooling with a minus sign you have to write. So A cools down faster in this particular problem. Okay, just wanted to highlight the mismatch of that word. Rate of cooling means minus dt by dt. Okay, so this slightly tougher multi-conceptual problem, right? On Newton's law of cooling combined with, okay, right? So try this one out and just give me your answer in the comments below with the timestamp. I'll come up with the solution of this as usual in AITS Select series in the coming days. So I request a lot of you students, instead of waiting for the video solutions, try to go through the comments of different people who are watching and producing the comments below, and I'll be replying to them. And from there, you can get the key or the solution for this also immediately if you want, because producing videos will take time. So instead of waiting for the authentic solution, I think you can uh, talk to each other and also me, and finally get your clarifications done. That's the whole idea of asking you to comment below. Okay, right? Comment your approach also in case you are doubtful so that I can correct it. Okay, so here's another interesting question. This is definitely a JEE advanced level question, but it's very basic level one. You should be able to guess through it. It appeared in one of the AITS exams. So just selected this for your practice. Okay, so till now, JEE mains has not asked any decent question on Wien's law of displacement. So just try to practice Wien's law also, right? Even though they're not there in your PYQs. Okay, so this is one particular question which is related to that law. Right? This is just at definitely JEE advanced level, but you should be able to answer this also if you understand what is Wien's law. Okay, right. So answer this one also below. This is very decent question. Okay, doable. All of them are doable. Not much difficult. Definitely not Olympiad level, but doable definitely. By the way, your JEE advanced level and your IOQ level 1 questions would be of similar level is what we are trying to think of. So people who are preparing for JEE advanced would be of a very good chance to actually be able to attempt the first level questions of IOQ. Okay, so next in line, or the next video that I'm going to produce, obviously is even more important than this topic 3 and even more exciting, and more ambiguities will be there that would be resolved, and more practice problem I'll try to come up with is heat and thermodynamics. Okay, I wanted to complete this entire thing in one video, but it, as you could see, so many models, so many questions, I didn't want to dilute it down. That's why I had to divide this into two parts, and heat and thermodynamics will start off with kinetic theory of gases, and then gas laws and thermodynamics, and also the extra syllabus part, which is the entropy and the second law. That's what we are going to cover. A lot of questions, a lot of repetitions, and a lot of ambiguities you could see in this particular topic 4 video, which I would bring it in 3 days time, I would say. All right, so please make sure that you are available at that point of time to go through this. Also check out the rest of the thermal properties and heat and thermodynamics challenges. I have made a separate playlist of that. I'll put the playlist link in the description below. Students who are interested in JEE Advanced and Physics Olympiads also will find very good challenges of this particular part. I've solved some of the Pathfinder questions also on heat and thermodynamics. So please do go through them. I'll be putting more and more solutions of Pathfinder of heat and thermal properties as we move along. Okay, so one abstract topic which students generally struggle with. And apart from JEE mains series that you are right now watching, there are other solution series that are going through parallelly in the channel. So in case you are new, Pathfinder solution series, Olympiad workout series, AITS, and result series, which solves doubts of the toppers and generally not answered in textbooks in an elaborate manner. You love the result series. If you're new to this channel, directly head to result series, watch the videos in the order of their uploading. So watch the oldest first so that you go in a sequence. There is always one video in my channel connected to another. I generally don't produce standalone videos, so there will be some sequence to the way that the physics family in this channel is being built. Okay, so in case you want to be part of this channel, so you're always welcome. And the kind of support I have been getting from the subscribers in this channel is very heartwarming, and with the kind of busy time I have, that is the only motivation for me to keep putting in more hard work in bringing authentic and quality videos, so that my satisfaction levels of teaching wider and wider number of students is fulfilled. Okay, so that's the only reason why I take time to produce videos on this channel. Okay, so please do like the video. Liked videos are pushed by YouTube algorithm to wider audience, thereby helping me grow my channel. Share it with relevant students groups in WhatsApp, Telegram, and Signal. I would be mm, highly obliged if you do that, and on my behalf request them to come and check out my channel. If they watch 2 or 3 videos, I'm pretty confident with the content that I have on my channel, that if they are serious students, they will not think twice before subscribing to my channel. Okay, so thanks for staying this long in your busy schedule. Thanks for giving me your time. Time is money, I understand that. Knowledge is power. Okay, so with that kind of spirit, I hope you will stay back and uh, support me in my next video. See you there.